Hi guys, it's Mr. Robeson here. We are back and we are looking at taking definite integrals today. So this is what's called the first fundamental theorem of calculus, and it basically means how to evaluate a definite integral. All right, so just a little bit of background here. So differentiation and integration, taking derivatives and taking integrals, are inverse operations. And the reason why this comes up is, well, if we just take a little section of a graph here, so the black line is the actual function that we're graphing, and we have a little delta y, a change in y in the y values over a little delta x section. If we are dividing those two, that gives us the slope, or it estimates the slope. Like it is an estimate, but it's basically the slope over this interval. All right. When we multiply those two sections, we're finding the area of this rectangle, which estimates the area of this little section under the curve. All right, so multiplication and division are inverse operations. All right, so that's why differentiation and integration are inverse operations. All right, because one of them has to do with multiplying, the other one has to do with dividing. All right, so this brings us to our first fundamental theorem of calculus. There will be two fundamental theorems of calculus. The first one here is just how to evaluate these kind of integrals when we have the numbers on them, and these are called definite integrals. All right, so if a function f is continuous from a to b, and capital F is the antiderivative of f, or what we sometimes call the integral of f, on a to b, then the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. All right, so in other words, to find the area under the curve, because remember this finds the area under the curve, that's what we found with the summation. So this is the area under the curve between a and b. All right, remember negative could be below the x-axis, positive would be above the x-axis. Right. What we do is we take the integral of this inside part of f, we get whatever that is, it's an antiderivative. We can leave off the plus c because it's going to cancel out if we put it in. Then we plug in the upper bound, so we plug in the top number here, and then we plug in the bottom number here, like f of b, f of a, and then we subtract between the two. All right, so here's a quick example. Integral of x to the third is x to the fourth over 4. And then we usually write it like this. We put a line next to it and say from 1 to 3. Because we've gotten rid of the integral sign, we need something to tell us, well, we're going to evaluate it from 1 to 3. This means we plug in the 3 first. So we get 3 to the fourth over 4 minus plug in the 1 to the fourth over 4. So that's what, 81 over 4 minus 1 over 4, which gives us 80 over 4. Divide that and we get 20. So that means the area under the curve, if we're looking at the graph of this, it's going to look something like this. It's going to go way up real fast. Let's just say maybe this is 3, this is 1. So the area of this section here, used to shading in it, but we don't really have to, is 20. All right. All right, so some more examples. So just practice in taking antiderivatives here and the notation. So we're finding the integral from 1 to 2 of x squared minus 3. So we take the antiderivative of this, we get x cubed over 3. We add 1, divide by that new exponent. Minus 3 gives us just a 3x. I'm going to put parentheses around this and say this is being evaluated from 1 to 2. We plug in the top number first, so we get 2 to the third over 3 minus 3 times 2. I'm going to put all that in parentheses because that's what we get when we plug in the 2. Minus, and now we're going to plug in the 1. So we get 1 to the third over 3 minus 3 times 1. All right, so let's see, this is 8 thirds minus 6. Then I'm just going to distribute that minus sign, minus 1 third plus 3. So 8 thirds minus 1 third is 7 thirds. Negative 6 plus 3 is minus 3. We can leave it like that, or we can change this to 9 thirds. So we'd have 7 thirds minus 9 thirds is negative 2 thirds. So we got a negative answer. Huh. All right, that must mean that more of this graph was below the x-axis than above the x-axis. All right, so if we take a look at this graph, let's see, we'd start off down here at negative 3. It would just be a parabola opening up like that. And we're going from 1 to 2. So 1 would be like there, 2 would be there. And yeah, let's see, this whole section is going to be a negative area. And then this little section up here would be a positive area. So those, looks like there's more of it down here, so that's why our answer becomes, or stays, negative in the end. Right, so we can get negative answers here for area. Seems kind of weird, you've never had negative area before, but now we do have negative area. All right, with this guy, remember we said constants can come out front, so I can just get the 3 out of the way, and I can write this square root of x as x to the 1/2, and then we can just do our power rule. So I'm going to leave the 3 out front. I'm just going to leave it out until the very end. So we get x to the one higher exponent is 3/2 over 3/2, or times 2/3, from 1 to 4. So leave the 3 out front. We'll plug in 4. We get 2/3 4 to the 3/2 minus 2/3 1 to the 3/2. 1 to anything is just 1. 4 to the 3/2 is we take the square root of 4, which is 2, and then cube it, so we get 8. So we're going to get 3 on the outside, 2/3 of 8 minus 2/3. If we distribute this 3 here, we're going to cancel out all the fractions, so that's nice. 2 times 8 is 16, minus this 2 gives us that the area here is 14. So the area under that curve, which would look something like this maybe, so it's a square root graph with an extra factor of 3. We're going from 1 to 4, so it would be this area here is what's being represented, and we're saying this area here is 14. That is what that integral represents. All right, and the next one here, secant squared. Oh boy. Well, I don't have to remember what this curve looks like. That's the great thing about this. All I have to remember is what its integral is, or what's the opposite of its derivative. So tangent has a derivative of secant squared. So that means the integral of secant squared is just tangent. So it's tangent of x from 0 to pi over 4. So that gives us tangent pi over 4 minus tangent of 0. Pi over 4 is 45 degrees. So that means the adjacent and the opposite are both 1. So that means that it's 1 over 1, or just 1. Tangent of 0 is 0. So we get that our answer here is just 1. So remember, each of these integrals represents the area under the curve from a to b of this function f of x. All right, a couple more examples. Absolute value. We don't have a derivative that gives us absolute value. All right, so what we have to do instead is think about this in terms of a graph, an area. So an absolute value curve is generally a v, and where it equals 0 is when this part inside equals 0. So we get x equals 1/2 is where this v, there we go. So it looks like that. So we'll have maybe 0 here, and 2 will be somewhere farther down, like that. So that means this, we just break it up into these two shapes that we can find the area of. So we have a triangle here, and we have another triangle here. To find the height of this triangle, we just plug in 0. If we plug in 0, 2 times 0 minus 1, an absolute value, gives us absolute value of -1, which is 1. So the height here is 1. The width here is 1/2. So the area for this triangle is 1 times 1/2, and it's half of that, because it is a triangle. So the area of that triangle is 1/4. So this area is 1/4. All right, this length here from 1/2 to 2 is 3/2. If we plug in 2 here, absolute value of 2 times 2 minus 1, so that's 4 minus 1 is 3. Absolute value of 3 is 3, so this height here is 3. So the area of that triangle is 1/2 of 3/2 times 3. So we get 9/4 for this guy. So the area of these two sections will be the integral, so we just add them up. 1/4 plus 9/4 gives us 10/4. We don't have to reduce fractions. If you want to, you can. If you want to divide, you can divide, but there's our answer right there, 10/4. Next one, find the area of the region bounded by the graph y equals this guy, the x-axis, and the vertical lines x equals 0 and x equals 2. Well, we could graph this. It's just a parabola. It's going to cross here at 2. It's going to open up. It's going to look something like that. All right, I graphed it before class, so I know. And we're going from this curve to the x-axis, so this is our x-axis, we're going from 0, x equals 0 is this line right here, x equals 2, maybe there. So we want to know what's this area in here. All right, so that area is represented by the integral from 0 to 2 of just that function, 2x squared minus 3x plus 2 dx. All right, so we just integrate that. So let's see, this would be 2x to the third over 3 minus 3x squared over 2 plus 2x from 0 to 2. Plug in 2, we get 2/3 of 2 cubed minus 3/2 of 2 squared plus 2 times 2 minus, if we plug in 0, we get 0, 0, and 0. That's one of the good things about plugging in 0. It's usually pretty easy to do. So we get 2/3 times 8 minus 3/2 times 4 plus 4. Let's see, those can cancel, give us a 2, so that's going to be 6. And let's see, 2 times 8 is 16/3 minus 6 plus 4. So that'd be 16/3 minus 2. 2 we could rewrite as 6 over 3, which would give us 10/3. Now, if you're doing the AP exam, you can actually stop right here on the free response. As soon as you've got it as it's just numbers, you can leave it as that. But for this class, if we're working out stuff for tests and quizzes and homework, practice simplifying, getting a nice number answer. All right, because that's what I want on test, is just a nice number answer. All right, so that's it. That's how we do the fundamental theorem of calculus, and that is how we evaluate definite integrals to find the area under a curve or between a function and the x-axis.